So I just recorded this entire video, and just realized that I recorded it with my mic muted. So we're gonna give this another try here because this is a really fun topic. Okay, so we're gonna solve this question here, and this is an alternative way to solve this differential equation, right? This one over here, and we're gonna do this just to test this assumption that we're trying to find a constant k such that y equals y1 of t, which is this equation right here, was solved, plus k is a solution of equation 1. So to do this, to kind of get the idea, what we're really checking for is once we solve this differential equation, the constant that we have, that we end up with, does it appear here? I mean, it's an alternative way of testing it, right? So the way we start this off is, and it'll make sense what I'm saying as we go through this. So let's solve this equation first. So we're just going to do dy over dt is equal to ay minus b. Now, that's a really ugly b, but there's a really interesting way to solve this. So, and what I mean by that is, I'll show you right here. So dy, there's a mathematical trick we have to use here. So we're going to get ay minus ab over a. Now, you might be wondering, like, what's going on here? Or some of you probably know what's going on here. It's not too complex of math, but we want to factor the a out. That's what we're trying to do. We're trying to get the a out, right? And we can't do that over here. You can't just divide both sides by y minus b. That's not how it works, right? So to do that, we rewrite b as a times b over a. And this is exactly the same as just writing b. Because a times b over a, if you cross out the a's, you're just left with b, right? So you could rewrite b as a times b over a. This allows us to take an a out. So let's do that. So we're going to get dy over, by the way, my drawing tablet is a little messed up. That's why it's a little wonky and sideways, you know? So we're going to get a parentheses y minus b over a. So we've successfully taken the a out. Let's continue. We're going to divide both sides by y minus b over a. So we're going to get dy slash dt or over dt is equal to y minus b over a. Let me just correct that because this doesn't look too good. Here we go. B over a is equal to just a on the other side. Okay? So now let's continue. We're going to take the integral of both sides. So integrating this side, we get the integral of 1 over y minus b over a dy is equal to the integral of a with respect to time, right? So once we set this up and we get our answer, which, 1 over anything, the integral of it is just going to be a log. So natural log is going to be, we're going to get over here, y minus b over a is equal to, and here we're going to get a to the t times t plus an arbitrary constant c. To get rid of the natural log here, we're going to take this entire equation on the right-hand side to the exponent of e. So we're going to be left with y, and that's what we want, right? Minus b over a is equal to e times a t times e. Because remember, if you take the entire right side to the exponent of e, you can't, it's not going to be e to the at plus e to the c. It's going to be e to the at times e to the c. That's just how the property works, right? E to the c. Now, this entire e to the c, we're going to just rewrite as c. So really what we end up with here is y is equal to c, so the constant c, times e to the at plus b over a. So that's our result. That's our first result. And the thing to hone in on is the constant b over a. So let me just write this over here. We're going to get y is equal to c e to the at plus ba. And now I want you to just pay attention to this constant over here, okay? So I'm going to erase this so we can continue. That's our first result, okay? That's that differential equation solved. So now what it's telling us to do is to test this in an alternative way. And that's exactly what we're going to do, okay? And you're going to see that the constant is going to appear, but it's a really cool way how it happens. I'm on a Mac, so I'm using Krita, which is the software that, unfortunately I'm not on a Windows, so I can't use Smooth Draw, which would be a little bit more helpful right here. But every time I switch to Eraser, which is what I have to do here, I have to increase the scale to like, you see how big it is here? And every time I switch back to the brush, unfortunately, it doesn't just auto reverse back to whatever scale I had the brush on. It takes the scale of the eraser. So just bear with me here. We're just going to erase that out and be careful here. I'm going to turn off the eraser, and we're going to move the scale back to what it was. Wait, 1 second. I'm just going to enter it manually. 1.68. There we go. Okay, so now let's solve the second one, because this will help us understand a little bit better. Okay, so we're gonna do the same thing again. So dy over dt, and we're looking for this over here, right? That's what it says. Call the solution y1t, right? So dt is equal to ay. So now we don't have to do any trick to take the a away, because simple algebra, we could just do dy over dt, and just excuse my y here, divided by y is equal to a, right? And now we take the integral of this, and we're going to get, I'm expert at wasting space, is going to be 1 over y dy is equal to the integral of a dt, okay? So we end up with almost the same thing as last time, right? The natural log of y is equal to a times t plus an arbitrary constant c. Okay. Now all we're gonna do again is we need the y, so we're gonna have to just do our little mathematical manipulation. We end up with y on the left side, and y is equal to e to the at times, remember times, not plus, e to the c. This again will just turn into a constant c, so we're just going to end up with y is equal to c e a t to the at. Okay, that's our second. So we're going to write here y1 t is equal to c e a t. Okay, that's what we have. So now we're going to really understand what the question is asking us, okay? Let me, again, I told you guys, pain in the ass. I got to increase the size of the eraser. And then bear with me, okay? And the weird thing is if I go a bit higher, you'll already see it. It'll erase the question too. Okay, but we know what it says. You guys can rewind to see the question. I'm going to turn the eraser off. And I'm going to put in my scale back. Okay. So now, what this is really asking us is if we write this as y is equal to y1 of t plus k. So what does that look like? So now we have both of these things, right? So we're just going to assume k to be k right now. Y is equal to, and we have y1 of t, which is c e a2 plus k. It's really asking us, is k the same as b over a, right? We're trying to arrive at this exact same thing, but just in an alternative, with an alternative method. And so it's saying, test this assumption by trying to find a constant k such that y equals y1t plus k is a solution of equation 1. So what we're going to do is we're going to set the derivative of y equal to equation 1, which is ay minus b. So let's derive this. So we're just going to go for y prime is going to be equal to, remember this is just going to turn to 0 because the derivative of a constant is 0. And here we're going to get, so remember e to the x, the derivative of e to the x is just e to the x, but the derivative of e to the ax is going to be e to the ax times a, right? So in this case, we're just going to get e to the at times, it's just going to be e to the at times a, right? So we're just going to get a c e to the at, and that's it. And this turns to 0. So that's our derivative. But what it tells us to do is set it equal to ay minus b. So let's do that. So we're going to come over here, and it's going to be really cool. You'll see in a second here. We're going to come over here. We're going to set it equal to, we're going to write a c e to the at is equal to, and here we have ay. So remember, don't just write y here. Y is equal to this entire thing, remember? So it tells us what y is in the equation. So we just have to just read the question, right? So y is equal to this, it's y1t. So we're going to go parentheses here. We're just substituting y for what this entire thing is. And we already have this figured out, which is this, all right? So y1t is just c e a t and plus k, and we sub this y in for this y, so a times this y minus b. Okay, so let's expand the right side and see what happens. Just see it, right? Let's just see what happens. E at is equal to a c e a t to the eat to the at times a to the k plus k to the k minus b. That's what we end up with. And right away we can just set this left side equal to 0 because these are like terms, right? So this will just cancel out. So the left side will be ace to the at minus ace to the at is equal to a k minus b. Okay, now this is just 0. This is all just the 0, okay? So we're going to get 0 is equal to ak minus b. And now you could probably guess what's next. We're going to get b is equal to ak, and we're going to get k, which is what we're looking for to test the assumption, is equal to b over a. Okay, do you notice something interesting? That's exactly what we have over here. So k is the constant b over a, but let's just test that. Let's write this to the fullest, right? So let's just write it as it is in its definitive form. So y is equal to y1t plus k. So let's just write this out. Let's continue. Y is equal to y1t, like we know, is just this, c e a t, and e to the at, sorry, and here it says plus k, but k we just found out is b over a, so we're going to get plus b over a. And if you look at this equation that we just ended up with here, this is actually the exact same equation that we ended up with over here once we solved it, right? This is just an alternative way of solving this equation that tells us that k is equal to b over a, and it satisfies this assumption, right? Therefore, it may seem reasonable to assume that the solution of these two equations also only differ by a constant, and we see that that's true, right? So we're testing this assumption, and that's it. That's all we got to talk about here. Thank you.